Hey, Ken.
Yes,
Hey, you're earlier than I am, and I thought I was early.
I'm writing my housekeeping stuff.
Ah, okay. An excellent plan.
Okay, so share me. Give me a share.
Yeah. As soon as I do this, you have all privileges. There you go.
I've been practicing.
Okay, good.
Uh,
There we go. We got a half a can and a half a menu.
right. Right. And then I'm gonna change as soon as I do my intro. I'm gonna go to this cam.
There you go.
Yeah. And I learned something. I'll show you.
Okay.
Um, uh, I just have to hit go show meeting in the bottom, and I go between I'm are you going to how do I get rid of you? No, no disrespect.
Um, good question. Hide self view. Did I disappear or no?
No, still you're still the guy.
Um,
You
hold on. Let me see.
maybe I have you completely given me um privilege full privileges, or are you just sharing the host?
Oh, like I can make you the host. There.
Right, make me
Now I'm a
host.
co-host. I think. Actually, I'm not even a co-host.
See, I can't. You're still showing up.
Let's see.
Or just turn your camera off.
Am I that bad? Let's see. Because I don't see myself. I hid myself. So,
Turn your camera off.
okay.
It's in
There.
video. Just click
Yep.
video.
Yep.
Ah, shit. That's not going to work. It's not working. Ah, stop video. See, and I still get your,
My image.
yeah, that image viewing you and your child.
Hmm. I didn't know you could do that.
Uh,
Um,
Hide non-video participants. Huh. Stop video. I got it. It died.
what?
You're gone.
Oh, how did you do that?
Uh-oh. See, now I still have you when I say show meeting. Dadgummit. Maybe I can't do it that way. Nope, still doesn't work. I I got rid of your thumbnail,
Hmm.
but I didn't get rid of you. Because when I go between meeting, I still have that, you have the big picture. Let's see here. See what I can do.
And it says that I can't even start my own video because the host stopped it.
No,
If you go side by side speaker view, under view, upper right,
I am on speaker view. No, I don't see a way of getting rid of you.
I don't even see myself.
See, when I stop the video, I kill me.
Mhm.
Oh. Boy, I don't know. I don't know.
Well, I mean, if people shrink you down on the using that bar, then anyone who's on the right-hand side gets really small.
Let's see. Let's see what I'm sharing here. Oh, okay. Everybody sees me. It says what you are sharing
Mhm.
is me and the
Block diagram.
presentation.
Right.
Okay. So I don't care. That's what I want to share.
Okay. So I still
Looks
can't
good.
turn my video on unless you make me a co-host. Oh, I can do that. I hit reclaim host. Ooh,
You're back.
I'm back.
You're now the host again.
And now you're the co-host. Powerful.
Well, I don't know.
Yeah, you do. This will be fine. People will have
Yeah.
a great time. And you know what? They can walk away knowing that they got their money's worth. Right?
They did that.
You know?
Yeah.
And maybe slightly more. No shame in that.
Okay, so you're gonna do the intro, right?
Yep.
All right.
What do you want me to say? Hey, this is Ken.
Whatever comes to your
This is Ken.
brain.
He knows a lot of shit about a lot of stuff.
Oh God.
Today he's going to divulge some of that shit to us
I'm gonna try.
and make us smarter than we were.
That's right. That's the goal.
Yeah.
I cannot tell you how many times I rearranged that slide presentation.
Yeah. And you know what's fun? You're the only one who knows whether or not it's good or not.
Yeah.
Hey, have you ever seen Idiocracy?
Opera?
No, the movie Idiocracy.
No. What are you doing now? Oh, you're showing it to me.
Let me see. Unshare. Let me see some. Share sound. Okay, here we go. State of the Union address 500 years from now.
Sit your monkey ass down. Chill out.
I'm inspired by this.
Shit. I know shit's bad with all that starving bullshit and the dust storms and we running out of French fries and burrito coverings.
Yeah.
But I got a solution.
That's what you said last time, dipshit.
I got a solution. You're a dick. South Carolina, what's up?
That's That's what I thought. Now, I understand everyone's shit's emotional right now, but listen up. I got a 3-point plan to fix everything. Number one, we got this guy not sure. Number two, he's got a higher IQ than any man alive. And number three, he's gonna fix everything. I give you my word as president. He'll fix the problems with all the dead crops. He's gonna make them grow again. And that ain't all. I give you my word. He's gonna fix the dust storms too. I give you my word. He's gonna fix the economy. He's so smart. He's gonna do it all in 1 week.
President Camacho stood before the world and promised everyone that Joe would solve all their problems. He would not only end the Dust Bowl and heal the economy, but he would cure acne and car sickness as well. And if he didn't, President Camacho made another promise. He would kick Joe's smart balls all the way up to the roof of his smart mouth, and then he would throw his brainy ass back in jail.
So I'm inspired whenever I think of what I'm going to say. I just think about that.
Okay.
You've never seen that movie?
No.
Oh, it's the most brilliant movie that represents I guess, a social satire on what's going to happen to the planet if the morons take over.
Not far from the truth, buddy.
No, it was 2006.
I
And
know
it was supposed to be it was supposed to be 500 years in the future.
Yeah.
And you watch it now and you're like, oh my God. Oh my God. That's now.
Reality.
Yeah.
Yeah. Yep. Every day.
Every day.
It's horror. I mean,
It's just,
when you have a Supreme Court that's totally out of control.
mhm.
From what I mean, you get they get these guys on these from Harvard, these scholars that really know. Actually, one of the scholars was the teacher
Mhm.
of the Supreme Court justice. I forgot which one. And he's going on about all the decisions they're making and how totally out of line from the Constitution. It's just,
Mhm. Yeah, but who's going to stop them?
that's it. How do you
That's what
stop
you get.
what?
You get what you get. So Ken,
Yes.
so in better things, I actually almost have a voice again.
Yeah, pretty much.
Yeah. I mean, it was a week ago, it was non-existent.
No.
So
I need to get you a new camera.
why? This is a good camera. No?
You're out of focus.
Am I?
Terrible resolution.
Really?
Yeah.
Well, this is the camera that I take on the road with me, so it might get bounced around a lot.
No.
Well, it used to be a nice camera.
But look at that compared to my camera.
Well, yours is a really nice camera.
Yeah.
Is that in focus? Because I'm staring right at it.
Not a bit. I'm giving you an eye exam,
Yeah.
but it's not a bit.
I'm curious. I'm curious if this thing can replicate a $50,000 eye exam. Can you see my retina in there?
No,
Funny, I can.
you can?
Yeah. I see the blood vessels and everything.
Terrible. Totally out of focus for me.
Yeah. That's so cool. I can see my own retina. I see the reflection of my own retina.
Now they're going to ask me, what did you do prior to the meeting?
You know what? it's experimentation.
Yeah.
Of course, I can't see out of my right eye right now. Do you know when I was in third grade, I once went up to the desk of my teacher's desk, and I looked at the stapler and I went,
What'd you do? You stapled a finger?
you know why?
No.
Because I said to myself, I guess, I wonder if a staple would coming out of a stapler would puncture my finger. And I think I said, ow, that hurt.
So you chalk that up to being inquisitive,
Completely.
you know.
I mean, I was a very, very curious child.
You know, all of a sudden you popped up in the window above yourself.
I did?
Yeah, alongside me.
That's weird. Although I see you up there too. So,
Yeah, we're both up there.
along with Tyler Parsons.
No,
Yeah, I get Tyler Parsons there. Maybe that's my view.
that's your view.
Uh-oh. Tyler, your audio is very Mickey Mouse.
Unplug your camera and plug it back in. I had a video conference with a guy in the Netherlands to align and what he always did when he got that was unplug his camera and plug it back in, and it took care of it.
That's weird, isn't it?
It's the first thing I've ever seen. Gonna do it. See what happens.
Probably going to work, right?
Yeah, should. It's weird.
Do you remember seeing during COVID the Zoom meeting where they were on a meeting between like a couple of attorneys and a judge, and one of the attorneys, apparently his kid had gotten onto his computer or something, and his head had been replaced by that of a cat. So, Your Honor, really, I know it may look like it, but I'm not a cat.
So everybody's going to be on mute, right?
If we make them that way.
I think we should. If it's as well attended as you think it is,
Well,
there's going to be a lot of background noise.
potentially, yes.
Yeah.
Do-do-do-do.
God, I'm worried
Oh,
about.
now we got two Tyler Parsons.
I don't have any.
You don't have any?
Any.
Go to gallery view.
I still. Oh, here he is. He's black. I mean, he's no video. Tyler, turn on your video. He went away again.
King of the road. Oh, look, Ron Files coming too. That's good.
I don't know where you seeing these people. I guess because you're a host.
No, well, I'm looking at the
Go
registration
ahead,
list.
Tyler, say something.
Is that any better?
Perfect.
Yes. Welcome.
See?
That was very weird. It was the Mickey Mouse sound.
This last time, this guy in the Netherlands, his name is Yap, Jaap.
Yup.
Every time I would connect with him, which was daily, to work on this Tektronix spectrum analyzer, this would happen. And I never heard of it before. And he'd say, oh, that's no problem. I just unplug the camera and plug it back in. Boom. And it would work. So did that fix yours as well? Tyler.
I unplugged it and it went gunny bag, so I restarted the meeting.
Oh, well, but in essence, you plugged it and unplugged it and plugged it and the meeting.
Yeah, I'm going to mute and also stop my video so you don't have to watch me eat dinner.
Okay, sounds good. Just as long as you can see me, that's good news.
I'll be back eventually.
All right. That's the mute. That's the video. Hot dog. I'm going back to speaker view. Shit, all I got is Tyler Parsons. What?
Uh-oh, did we lose Tyler?
Yeah, he went away.
Oh, okay. But I mean, he's still here. He just,
Yeah.
so I'm all out of focus, huh?
Okay, so I don't care what all I have is everybody see. Do you see just me and my presentation now?
And just I'll shrunk down on the right-hand side. I
Yeah,
have,
that's okay.
yeah.
that
Yeah.
nope, just the two of us, right? Right now, just yeah. These are going to be the attendees are going to be strung here on the right. Boom. So I'm just going to leave this up. And I can change cameras on the fly. Like that. Ba-boom. And you guys can see, you see both. You see the new camera. Yep. And the presentation. Exactly what I want. Back to me. Maybe. Yep. Show meeting. And I see. And you're the speaker because when I'm in speaker view, you are the big kahuna. And now you have no audio.
Oh, I muted myself. There we go.
Yeah.
Go down and scroll through the tutorial, would you? Just one slide at a time.
Uh,
We're still looking at the first slide.
can't move it.
Can't?
Okay, wait a minute. Hide meeting. Now.
Yep.
Right?
Yep.
Yep.
Okay, hold on.
Oh,
Okay.
you stopped me sharing.
I did.
Yeah, it went away.
It wasn't me.
Oh. And I did it. Now God.
You're still co-host.
Escape. Oh, I'm out of, somehow I kicked myself out of share.
Huh. There we go. Hey, Tharpy Mark is here.
David.
Okay, there we go. Scroll down one slide. You should be able to scroll down through one slide at a time. There we go.
Yeah.
Okay, hold on. I just want to
What?
go back up one. Nope, you went up too far. You keep missing that one.
Which one do you want?
Keep going. Keep going. Stop.
What's the big deal here?
I just want to see what if I can read the font on the smallest lettering. Yeah, I can. I've got a 17-inch laptop screen.
Oh, well, all you need to do is stretch it.
Can I? I don't think I can.
I mean, that's what we talked about when you were here. You can stretch from side to side, can't you?
Mm-mm. Remember,
Why?
this is the you carrying side by side. You're equal size with it.
Well, I thought it was the viewers could drag it back and forth. Remember when we talked about that?
Now I can drag the whole thing back and forth, but you're split 50-50.
God damn it.
Well, no, that's actually okay, because what you can do is you can change the view to the tutorial.
Okay,
You can change the view to the tutorial only if you want.
let's see who's here. Me,
They're
you,
letting, they're letting everybody in.
Richard,
IDX, yep. Russ is here.
Russ. And they're all muted. That's good.
I don't know. It's so hard to keep Tharp quiet.
Shh. Ham's quiet. That's a oxymoron.
Well, it's Tharp too. You know Tharp?
No.
He's our division director. Hi, Mark. Hello, Mark. Hi, Gary. Hi, Mark.
They're muted, right? I think
No.
Are they force muted?
No,
No.
nah, everyone here is pretty well behaved.
There's a
Mark.
Richard.
Mark, are you there?
We are all here,
Hey,
waiting with bated breath.
me too. Baited with cheese, I hope.
8 participants already. Oh, actually 6.
Well, we got 43 people on the list.
Gary, hell. I'll be go to hell. Look at that.
Yeah.
You guys know each other?
Oh yeah. Old home week. Yeah, we're K4 gurus.
Ah,
No. Well, he's the guru. I'm just K4.
Guri.
So I think I have an RS-35M,
Everybody has. Well, actually, I don't.
but that does not work. And I also have, I think, a 15 that doesn't work. And I have about 3 or 4 of these things that do work.
They didn't make a
But
15.
the thing that goes
I
busted
mean,
in most of them is the chip. So if you get the new chip and jam it in there, usually it works. Although the 35 I've got, I'm pretty sure it's one of the pass transistors that is screwed up.
So they make the series that I know of is a 12, a 20, a 35, and a 50.
Yeah, I think I got a 20 and a 35.
I have a 50, a 20, and a 12.
Yeah. People get tired of them and they essentially give them away. But they're good. Although the one of them I've got is got a lot of ripple in it, a lot of hum. That's not good for radios, but it's good for charging batteries.
Hmm. Yeah.
That and you got to retrofit them because usually they have the diodes that are exposed on the bottom of the chassis. So you got to cover them with plastic or something so you don't set them down on something and short it out.
Right. Yeah.
Well, I hope people realize that it's today. You can only do so much.
I thought it was June 2nd.
Yeah, I thought I fixed that.
June
You saw?
2nd.
I fixed that.
9
Yeah.
participants. Russell Williamson.
So we're gonna ask that everybody put call signs up with them, with their name.
I have to do that if I go on the K4 Zoom meeting, or they kick me off.
Do they really?
I'm serious. You have to have your call.
Well, it's a lot more unique than a name. So
So I assume that the only thing that people can see is me and the presentation. Is that correct?
And if we slide the screen all
Yeah,
the way to one
we can
side,
see everybody else who's got their video on.
right?
Okay. All right, looks like it's almost witching hour here.
Yeah. Wait another minute.
Okay. 11 people.
So far, like I said, we had 43 sign up, including us.
There's Dave.
Hey, Ken, I have one question about the 35, that power supply.
Yeah,
Why is the switching transformer so big? No,
there's always one.
There's always one.
That's to exercise your arms.
and the meeting's not over yet, Ken.
Wait, you're saying, Dave, that was just a shot across the bow?
Rhetorical question.
Scott, thanks for organizing this. This is nice. I'm glad to see this.
Well, I just had this bizarre idea that everybody was because like, I mean, I've studied the RS-35 schematic.
Everybody
years.
has one of these.
Yeah, exactly. And there are occasions when, okay, so I fought against an old Lambda power supply years and years ago that should have worked, and I never got the thing working. And I don't like giving up, but eventually I gave up. I just didn't know what to do. Like, I mean, I had full schematics on it. The thing was really built like a
Yeah, but
tank.
Lambdas are much more complicated than a
One thing-
Astron.
One thing I know from my years and years of experience is that you can have the best schematics on the planet, but when you're troubleshooting something, you should know what to expect when you probe it, either with a scope or voltmeter or what have you. You should know what you expect to get at that point. And
Yeah.
if you don't, it's meaningless.
Mm-hmm.
And that's where the skill comes in, is to know what you want to you expect to see, and when you don't, you can interpret what that means.
Well, and I will say that I was at the beginning of the era of the throwaway board.
Yeah.
Right. I've troubleshot stuff down to the component level, but it's really hard to find anything that you can do that anymore with.
Mhm.
You know, basically you just replace a board. You know, if the black box, if the black, if a
Haven't
little,
learned anything.
well, right. If the black, well, you've troubleshot down to that point, but if that part of the black box isn't working, you get a
Yeah.
new part of the black box.
Right. I gotta lower the temperature in here.
Ken, I'm not lurking. For some reason, I can't get my video camera started, so you won't have to look at me tonight.
That's fine. If you can see me, that's the main thing.
Yes, that's the important thing.
Yeah.
And again, if you're just getting here, if you can modify your name to include your call sign, that would be really helpful. And okay, so it is 6:03. To me, that's about time to start. And I know we had Ron. Oh, there's Ron. I hope Ron's picture comes up. So, Scott N7JI. I'm ARRL Oregon section manager. Some of you might know who I am. Some of you might rue the day that you met me, et cetera, et cetera, et cetera. But anyway, I one of the things that we've been trying to do here in the Oregon section is work on coming up with some pretty cool programs and stuff, and trying to build up our technical base, and trying to build up numerous different other functions that are part of the field services program. with ARRL, and one of them is is technical coordinators or technical coordinator. And another one is coming up with technical specialists who can help out in various different ways for ARRL members when the time comes. So we have right now Ron File. I hope I got that right. Ron, are you able to do you have video? Are you able to put audio on?
I don't even see.
Okay, I unmuted, sorry.
Okay. Any video tonight or no video tonight?
I turned my video on, but didn't test it, so I guess I still have to allow. Let me hear it is. Okay, start video. Got it.
There we go.
Haven't done Zoom for a while.
Yeah. So anyway, Ron, looks like you might have your camera shutter closed because it's just blue.
I don't even see it.
I'm sorry, say again.
Your screen is just nothing
There
but
it is.
blue in case your camera shutter is like closed or something.
Well, my camera is turned on. Let me see.
Looking at a blue screen.
Yeah, maybe it's taking some time. It says video's on. It says mic is on. Hmm.
Well, anyway, we'll go with the audio. So
Right.
Okay.
Ron is our technical coordinator in the section. And Ron, since we haven't gotten to do this before, would you like to introduce yourself and talk about the technical program that we're running?
Well, we're trying to rebuild the technical specialist for the Oregon section, and we keep getting more people. I haven't posted them yet, but we keep getting new people. I picked up a couple at the Seaside meeting a few weekends ago, and it's just wonderful that people are interested. I think COVID really knocked back a lot. Uh, we're starting to get people in different areas, and I'm trying to organize a web page or something that Dave uh, Eugene there can incorporate into the web pages so that could look up people who's a technical specialist in various areas and either email them or give them a phone call and get technical help. I'm sure there are all kinds of people out there with specialties, and this is a wonderful thing for the fraternity of ham radio operators. Can you hear me?
Yep.
Yeah.
Unmuted.
Okay.
There we go.
Oh, okay.
So, okay, well, I am going to introduce Ron. Ron. I'm going to introduce Ken over there, W6SKI, who after 25 years or so of living in the same area, we finally actually met each other face to face on field day this year, which is just insane. We only live a few miles apart. You know, we must have seen each other without our call signs on at some point over the last 25 years and just walked right past each other without even thinking about it. But anyway, Ron spent a lot of time in his Ron has spent a lot of time in his life doing analog circuit design,
Ken.
with a big focus on power supplies. And I'll let you go more into that, Ron. Go more into that, Ken.
Okay. Yeah, I kind of fell into this career. After I got out of the Air Force, I started working for Hewlett Packard as a technician and in the brand new computer division. And for some reason, I fell in love with power supplies versus the rest of the computer. And when they needed somebody in the lab to work on power supplies, I volunteered in a heartbeat. And so the rest is kind of history. I'm not going to get into it, but basically I spent my entire time designing power supplies, not linears. We're on the cutting edge of switchers, but I don't have a problem talking about linears if it's necessary. And if people are inquisitive about my accent, it's a Bronx accent. So, anyway, see me later if that means anything. I first a couple of housekeeping issues. Questions will be at the end. When Scott and I set this thing up, you may or may not have the ability to change the proportion of the slide presentation versus the video on your screen. We thought we had that working, but I'm not sure. You can experiment with it and see if you can find a slider between the slide presentation and the video so that at any point you can make either one of those larger so you can see it better. The slides will be available for your asking at the end or by email as a PowerPoint presentation file. And I must apologize if my presentation is above or below your skill level. It's very hard for me to determine what level I need to have this at. So I'm going to take a shot at it and see if it's meaningful. I hope it is. First, I'd like to, at the bottom of the screen, you notice that I want to thank Ron K7TBT for the use of his RS35M power supply. When I switch between my puss and the power supply, which I'm going to do most of the presentation. So I want to show you parts, what the components look like that I'm talking about. Okay, first we want to talk about why the RS35M is called a linear power supply. And that's because the transistors that regulate the output are used in the linear region. As you'll see in the next slide or subsequent slide, you'll see that there's 3 states of a transistor, 3 operational states. And we'll talk about that later so I can better understand, you can understand the workings of the beast. Linear versus switching power supply, why would I care? A linear power supply, which is highly dissipative, because most of the energy that's dissipated to regulate the output goes off as heat. And so that's why you'll see most of the parts tied down to the frame of this thing. Typical efficiency, 50 to 70%. Switching power supplies, on the other hand, are in the other 2 states of a bipolar transistor, which is on, you'll see on and off. And their efficiency, when I first started designing them, was around 80%. Nowadays, with all the great parts that we have, components to use, they're up around, in some cases, 96%. And that's an incredible difference between the 2. And of course, there are trade-offs. As in everything in life, there are trade-offs between the switches and the linears. And I know you guys probably know these trade-offs, because if you bought a switch mode power supply that is not from a reputable company, you've seen birdies where they gets into your receiver, the switching frequencies or harmonics of the switching frequency. Okay, here's the block diagram of the RS35M. All right. You have your power input, and your the next block is the power transformer, where you step down the input voltage to a voltage that is higher than the highest output voltage necessary, plus some margin. So in this case, I think it's around 18, well, yeah, about 18 to 20 volts. It's stepped down to, and then you rectify it. And I'm going to go through rectification. And then you regulate it using the pass transistors in the linear mode. And then that gives you the output voltage, and you sample the output voltage, and you go to the regulator, and the regulator then controls the output transistor. This is called, as you'll see later, closed loop operation. And I'll go through the way the regulator works to achieve that. And then, of course, you have the OVP protection circuit on the output that looks at the output and says if it exceeds the level, goes to an unsafe level, this OVP will fire and cause essentially a short to eliminate the output voltage. And from what I've seen so far, these power supplies, the problem with these power supplies is false triggering of the OVP circuit. Okay, first thing, I hope you can all see this. Yes, you can see it in full.
Yep.
Good. And I'm going to switch to the other.
I don't know if you can kill your video so we can have a full screen for the display video. Oh, there you go.
How's it? What do you got now?
2 display videos. The power
Right.
transformer and a picture.
That's it.
Okay.
Can you slide? Is there a slider between the two that you can move? I don't know who's talking, but
There's not.
there's not a slider. Yes, I can go like this. Whoops, no, I can't. Let's see. I knew a way to do that. Let's see.
Is anyone having a problem reading? I can read it okay as it is.
Yeah,
I'm okay.
I'm fine with it the way it sits. It looks great.
Not, oh boy.
Go with it. Just go with it, Ken. We're good.
Okay. All right, so, no, I don't have my, oh, wait a minute. Okay, so now we have this beast of a transformer, as you guys know. It's this big thing over here. Can you guys see the laser pointer at all?
Yep, no
Yep.
problem at all.
Yep.
Yeah, it's fine.
Okay. So this transformer is at this frequency, which is 60 hertz. Iron is the best way to couple the primary and secondaries together. Let me see if I go to the presentation because I'm losing myself here. Okay, so first thing I want to tell you is that you cannot have DC. You cannot pass DC through a transformer. I don't know. I just thought of that. I just wanted to throw it out. Obviously, you need, and I'll go through inductors in a minute, but you need alternating current to go to operate a transformer. And voltage is increased by the turn or reduced by the turns ratio. And current is increased or reduced by the turns ratio inversely proportional to the voltage. Okay, so power transformers have very minimal losses. They're very, very efficient devices. And so we tend to use this formula here without any, for the most part, where the current times the voltage is always equal to the current times the voltage. So in other words, power in equals power out. And so what's all the transformer does is it reduces the voltage by the ratio and increases the current by that ratio. And the other part I wanted to bring up is just something that radio works like a transformer. In other words, a transmitter is like the primary of a transformer. The air is the core, and the receiver is the secondary. And the signal, the carrier frequency, is the frequency of the primary and secondary, right? So the information just rides on that frequency. In this case, 60 hertz, but in case of a radio, it's higher, obviously. Okay, so I just thought that I want to give you the concept that radio it can be thought of like a transformer, where again, the medium is the air rather than an iron core. Now, what does the iron core do? Well, it increases the coupling. Whenever you put current through a wire, you get a field. And when you create multiple turns around a core, you increase the field. And then the secondary is tightly coupled to the field. And so when the field collapses, as it does every 8.33 milliseconds, that field, for the most part, is induced into the secondary. Okay. So here's the actual schematic of the RS-35M, and I have to apologize. They show bridge rectifiers. That is not the case. In the actual supply, they have just large. Can you look at my
Yep, we're looking at some big diodes.
big diodes mounted to the chassis as heat sinks? All right, rather than these bridge rectifiers that are, if you look at it closely, you'll see they just wired the bridge to look like a single diode. Two single diodes here. So the other diodes, D1 and D2, are housekeeping diodes. And they are very small diodes that are mounted on the, right here, on the regulator board. Can you see that, everybody?
So is this to say that this particular power supply is actually built with half-wave rectifiers versus full wave?
It's full wave. It's full wave it's half wave, half wave rectification.
It's full wave rectified, but it looks like the secondary, the transformer, would be center tapped, and then
right
on one half
That's
the
right.
cycle, one diode is used, and on the other half of the cycle, the other.
I'm going to show you that right
Yeah, okay.
Here it is. So this is the equivalent circuit of that. So the idea is you have the secondary, which is reduced, this this waveform is the secondary of the transformer. And then after you go through the diodes, the negative portion is flipped so that it is in the positive direction.
With the key being that the secondary is center tapped.
Right. There's the center tap right there. Okay. So whenever if I drew plus and minuses here, when the diode, the D1 is forward biased, you have a conduction. And then when D2, you also conduct, but you flipped it because the polarity is reversed between the center tap and the D2 versus the center tap and D1. And so the output looks like this. Okay. Now, I do have a little section here of how a diode works. And I don't know if this is meaningful to anyone, but over here I have a tube. On the left-hand side, I have a tube. And the way a tube rectifies is by electrons being boiled off the filament and then going through the vacuum and being attracted to the plate. All right, you can't get electrons boiled off in the other direction. So this is a way of getting a single flow, single direction flow is what you need. The case of a diode, here is the diode on the other side. Oh, the other thing I want to first say is that I don't know if anyone, if this is probably common knowledge, but I needed to say it here, that conventional current flow is opposite from electron flow. So the way we think of current flowing all the time is actually not reality. It's the electrons are flowing in the opposite direction. And so I went on the internet and I said, how did that ever happen? And on this, and here it is, it tells you that
it was Ben Franklin.
Right.
It goes back a long way.
Before people realized that electrons were negatively charged, they assigned the current flow in the opposite direction. And I needed to say that to explain diodes. That's the only reason I mentioned it. Okay, so in the case of a PN junction diode, which is what this is, you essentially have an N region that is filled with electrons. Negative, electrons are negative. In the P region, you have holes, all right? And so when you apply power to this thing, the electrons and forward bias the diode, the electrons in the N region push we call the depletion region. And this depletion region breaks down and current flows through the diode. If you reverse the voltage, you can't get electrons in the holes. You know, they won't get to and deplete the region. So your diode has no current flow in that direction. So once again, like the tube, you've got a unidirectional or a semiconductor. Somewhere I had that in the presentation. I forgot where I put it, out of order, I guess. But the reason it's called a semiconductor is because it's not a wire. It does not conduct all the time. It's a semiconductor. You know, we use a lot of these words, and we really, bipolar, transistor, we use a lot of words, and quite frankly, we don't understand why these words came from. Now, for example, let's talk about the transistor. I'm going to jump a few slides. Why is the transistor called a transistor? Well, the three guys at Bell Labs that invented the bipolar transistor felt that the way to adequately describe it, because up until then they were dealing with voltage control devices like the vacuum tube. And they said, well, this device transfers resistance. Because we're passing a current through, and we're literally in the active region, the linear region, we can vary the resistance. By passing a current into the base, we can get the transistor to conduct and change the effective resistance. So transfer of resistance evolved into transistor. And what are the three states of a transistor? Very important. Off, infinite resistance. On, no resistance. And linear, resistance is variable. So the first two states, the first and third states is the switch mode state. The second state is the linear state. Okay? So the bipolar transistor is current operated, and the MOSFET, which evolved much later, is a voltage operated device. And by the way, as I mentioned before, the vacuum tube is also a voltage operated device. Okay. So let's go back here. We got the diodes conducting. And now we're going to talk about getting this waveform here into DC. This is not what we want at this point. We want DC, not pulsating DC. We want DC. So the next thing we do is we go into a capacitor. Let's see what I can find it on the circuit up here. We go into this capacitor right here, C5. Okay, C5 where's mine? Whoops. Excuse me, I'm having technical difficulty here. Well, I lost the camera. I'm sorry to say.
We can still see the picture.
Yeah, I know you can, but I can't.
Oh.
So I'm in trouble. Anyway, so I'm going to just assume that you can see it.
Yep, we're good.
All right. So the capacitor we're talking about that's going to do the convert AC, the pulsating DC to DC is this bad boy here, this big blue with a black top. Everybody see it?
Yeah, you might want to tip the camera down slightly.
Okay.
There we go.
All right.
30 meters is.
What? Oh. So all right. Now, here's a little crutch that I've always had all my life. It's called Eli the Iceman. I don't know if any of you have ever been exposed to Eli the Iceman, but it's just an easy way to remember that the voltage leads the capacitor. I mean, voltage leads the current in an inductor, and the current leads the capacity, the voltage, God, in a capacitor. So the person that told it to me who said, "Oh, that's Eli the Iceman." Okay. Voltage leads the current in an inductor, and the current leads the voltage in a capacitor. All right. So in every case, depending on what resistance and what capacitance value you have, in approximately 5 time constants, it will reach, in the case of a capacitor, it will reach the voltage. It will be fully charged in 5 time constants. If you look over here on the schematic, you take a voltage and close the switch, and here's the R and the C. Typically, the R is very, very small. In our case, it's just the ESR of the capacitor, equivalent series resistance of the capacitor. And so, since this is so small, the inrush current is horrendous. And that's why when you turn these supplies on, they tend to make a bang or a bong sound to them. And the reason is that there's so much current rushing from the input power line through the transformer, and the transformer is just seeing this huge, huge amount of current because the capacitance is 0. So current is maximum, hence a lot of inrush. Okay, so, right? And so, unfortunately, what we've done in a lot of designs is what we call soft starts. And the cheapest way to do that is to have a thermistor on the input, where when the thermistor is cold, when you first turn it on, the resistance is high, and it limits the current going into the supply. And then as the load increases, the output load is applied, the thermistor gets warm, and it's a negative temperature coefficient, and its resistance drops, and all is well. Of course, if you were to turn the supply off and on very quickly with the thermistor hot, that would not be a good thing. But normally, this works. A lot of other linear power supplies, not linear, but excuse me, linear amplifiers use a resistor and a relay, where the resistor gets switched out by the relay. So initially the relay's off, resistance is in series with the load, and then when the voltage comes up, the relay closes and you're off and running. So this is ways of inrush limiting. Unfortunately, the RS-35M has none of that. So you're going to get the bong of the power transformer literally jumping out of its, I don't know, jumping.
If I can ask, how much of that is due to the capacitor, and how much of it is just due to the fact that it has to magnetize an unsaturated transformer?
Most of it's the capacitor. You can try it. You can try it without the capacitor, and you'll see it's virtually nothing. There is some of that, but it's more the shorted capacitor is out there that causes most of the inrush. Okay. See, okay, so capacitor stores energy between the plates. The substance is called electrolyte. Okay, and an inductor is just the opposite. The time constant is R over L. And the nifty thing about an inductor is that when you first apply power, the inductance is maximum, and then 5 times constants later, it's saturated. So if you're using an inductor in every case, you want to stay in the active region, according to this, I don't know, 63.2%. I don't know if that means anything, but you want to stay out of saturation, obviously, because if you get into saturation, you don't have an inductor anymore. It's a wire. Okay. I've been through this. Okay, semiconductor, we talked about that. Okay, here's a bipolar transistor. And basically, you control the current from the emitter to the base by putting current in the base region. All right, so essentially the resistance between the emitter and the collector can be varied by the base current. All right. And here is a couple of symbols of bipolar transistors. In this case, I showed you a PNP, and the other flavor of it is NPN, where the regions are just reversed. Okay, closed loop regulation. Essentially, we've created the DC voltage, the unregulated voltage in. We've got the pass transistors, and I'll show you the schematic for that. Here are the pass transistors, right? And we're going to vary the resistance of these things to step the voltage down from the bulk voltage to the desired output voltage. Now, the reason we have these resistors, all four of these resistors, is to make sure that no transistor is starved for current, right? Because the forward voltage drop of each one of these transistors, regardless of the fact that it's the same transistor part number, they all have different forward drops between the emitter and base. And if you don't add these resistors in series with the emitters like this, you'll have one conducting harder than the other. So these resistors allow for the voltage drop difference in the emitter base region. Okay. Okay, back to this. So here are the pass transistors, and it creates the regulated output. A sample of this regulated output goes back into a regulator. And this is the loop that is created. In other words, if the output's too high, the regulator is going to lower the conduction of the transistors, raise the resistance, and allow the output voltage to drop. So here's the area. Here basically is the loop. Okay, see, these are the pass. This is the pass transistor. This is a driver for the pass, and this is an error amplifier. Now, the thing I want to drive home, an error amplifier is just a form of op amp, right? This LM723, UA723, that's in that chip that's on the control board. Right there. This chip here.
Oh, you got to tip the camera up again.
Oh, thank you.
There we go.
Okay. This chip right here is the UA723. It has a reference in it, and it has an error amplifier in it, and it has a small driver. All right. Now, what I say at the bottom is to me the point I want to drive home. An error amplifier's mission in life is to make both inputs equal. All right? If you can make both inputs equal, you have the correct output, because the reference is on one input, and if the output, and this is a simplified drawing, believe me, this is not exact. There are dividers and things like that, but if for this thing, let's assume the reference is 13.8 volts. It is not, but let's assume. And then this input has to also be 13.8. So this error amplifier is going to do everything in its power, raise and lower this output to increase or decrease the drive to the pass transistor to make that output, well, I mistyped, 13 volts. All right. So that is, to me, is the crux of this whole linear regulator, to have this loop to regulate the output. Okay, here's the schematic of it. Here's the reference on pin 6. Pin 5 is the input, the positive input right here. Okay. And then the negative input is right here. And it is and the pot is for adjustment, of course, but it's looking at the output of the supply. So the output is sampled here. It comes down through this divider network, and a sample of it comes back to the input. So whatever the reference is, I think it's somewhere around 6 volts, has to be here. So if you are troubleshooting this thing and you do not see 4 and 5 the same voltage, your loop's open. Very simple. Okay. This is a driver Q2 to increase the current out of the feeble output out of the regulator. And then eventually it goes up to the pass transistors. Okay. And that's pretty much all I'm going to talk about here. A lot of his stuff is protection circuitry, but not, yeah. All right, so there's that Q2, the driver coming from the regulator. Here are the pass transistors. All right, so now we're going to talk about OVP. The biggest problem in this supply.
Hey, Ken, can you go back up one slide?
Yeah. That one?
Yeah, there we go. Or no, the one with the pass transistors, with the 4 pass transistors in parallel.
Okay,
Nope. There we go.
Yep.
So is this actually a voltage output or a current output device? I mean,
well, these are current operated,
right.
but the output's a voltage. Why?
Okay.
Resistors. Think of these as variable resistors. They're in the linear region.
Okay, because we always think of a power supply as having to deliver a certain amount of current, and the number of pass transistors defines how much current it can generate. It can push.
Right, and the transformer and the rectifier diodes, everything defines how much current you can pass. Now the thing is that as the current increases, the voltage is going to start to droop. Right?
Mm-hmm.
And so the loop says, oh, my output is dropping, and then it makes the transistors conduct harder.
Okay.
No? You see? In other words, the resistance is effectively going to drop on those 4 transistors. So the drop from the input to the of the 4 transistors and the output is going to decrease to increase the to keep the voltage steady on the output.
All right.
What am I missing?
Hey, Ken, I could throw out kind of an analogy or a simplification, maybe, if you don't mind.
Go ahead.
If you think of it, think of the load on your power supply, whatever you have hooked to it, think of it as just being a resistor.
Right.
And this is a resistor divider. I have a voltage source coming out of my transformer and rectifier and filter.
Yep.
So I got a voltage. I want to drop part of that voltage in these pass transistors, and I'm going to drop part of the voltage on the load.
Right.
And if I've changed my power requirements in my load, effectively changing its resistance, then I got to change the resistance of this part of the divider to keep the voltage right. That
Correct.
makes some sense.
Yep.
As far as voltage versus current, it's just a divider circuit, basically.
Yep.
Thank you.
And can I say something?
Yeah.
If we had a bigger power transistor, we wouldn't have to have 4 transistors here in parallel with all of these emitter swamp resistors. We could just have one big transistor. But when they first started making these, they didn't sometimes have transistors that could handle the current, so they would parallel 2 or 3 or 4 of these, and in that case, they had to have the swamp resistors because bipolar transistors have a negative temperature coefficient. In other words, when they pass more current, they get warmer, and when they get warmer, the base emitter turn-on voltage shifts lower, so they're turned on harder. So they would, whichever one conducted the best or the warmest would suddenly suck up all the current away from the others by turning on so much it would burn out and the others would be sitting cool.
Right.
And by having these resistors, when one starts to conduct more, it sees a higher voltage across that resistor, which is in series with the drive to the base, and it then cuts itself back. So they all are self-regulating to share the voltage equally. You just have to have that resistor just big enough to swamp out that thermal coefficient of the base. Okay, I'm sorry.
That's it. I love it. That's good explanation. Thanks for the help. Okay, so back to OVP. First, I got to talk about the Zener. We talked about diodes, right? And as you probably know, well, okay, wait a minute. Where is it? Where's my Zener talk? Ah, there we go. Okay. So this is the symbol for a Zener. And a Zener is designed to start conducting or break down in the reverse direction at a specific voltage. This is different than a diode because a diode, normal diodes will also break down, but at a much, much higher voltage and a unpredictable voltage. What I mean by that is in most cases, we don't, if the voltage of a diode is significantly high, we don't take that into account. I mean, we take it into account when designing, but what we don't take into account is the voltage breakdown. We don't use it. Use it as in the active in the circuit. It's just something we have to deal with to make sure that it doesn't fail. In the case of a Zener, the way it's doped in such a way is that that breakdown is controlled. And so the Zener voltage is the actual spec, 5.1 volts, 6 volts, whatever the Zener voltage occurs when the Zener is back biased. All right. In the forward direction, looks just like a regular diode. So this is just a nifty thing that occurred to make a regulator, basically, to have a way of having a very, very, very inexpensive method of creating a voltage source. So we use that to detect when the output exceeds the desired voltage. What happens is the way we have it set up is that when the voltage gets too high, the Zener will break down and then current will flow. And that current will pull this gate. This is what an SCR really looks like. It is one component, looks like a transistor. I mean, in a case, has 3 leads, anode, cathode, gate. But in reality, what's inside of this is 2 transistors, a PNP and an NPN. And what happens is if the gate goes high, it turns on this transistor here, which then makes this transistor turn on. Current flows through the emitter base region of this guy, through the collector emitter of that guy, which then pulls this high, which then, what I like to think of it as the bootstraps, pulls up and latches. This becomes latched. So no matter what you do on the gate, high or low, you can do anything you want on the gate, this latch continues. And the only way to stop this current flowing from anode to cathode on an SCR is to actually take it through 0, or essentially stop the current flowing, and the latch will then break, be open. So that's why when you get an over voltage on the RS-35M, the only way to reset it is to turn it off. That's because the output voltage is sitting here feeding current through this latch. And this cathode is basically at ground, and that anode is basically at the output voltage. Okay, and the Zener is what's triggering that gate, pulling that high. And I'll show you the circuit right here. So the Zener is monitoring the output. The Zener breaks down, current flows through the emitter base junction of this transistor, which then pulls that high, and that high goes into the gate of the SCR right here. The SCR is tied to the output, and then eventually gets to ground, goes to ground right there. Is grounded right there. That's the output ground. So that's the SCR. Now, what I have done to fix this, due to the fact that this one I haven't looked at yet, but the other one, the SCR was mounted on the circuit board. In this case, the SCR is mounted on the deck right here. Whoops. I don't know if you guys can see that. Can you see it? Anybody know? See it?
It's kind of
Yes,
it's kind of
it's
tough.
down there.
It's
It's down there in the middle of that blue line. It's right behind at the very bottom of that heat sink.
tilt down on the camera.
Okay, there we go.
Right there.
Oh, there we go.
That's the SCR on this one. The other one that I fixed, it was mounted on the control board, which is crazy. But anyway, what I have done is I put delay. And my feeling is that the overshoot that occurs when the power supply starts up puts this SCR, the OVP circuit, in jeopardy, and it needs some delay so that the SCR doesn't latch before the output voltage settles. Now, I've checked the startup, the rate of rise from the startup to output, quiescent voltage. Now, from when you first power it up to the time it reaches its normal voltage, and it looks pretty smooth, doesn't do any overshoot, but my feeling is that when you get it just right, and your timing is right on the power switch, you can get some overshoot, and this SCR will fire. On the other one, this C102 was pretty remote. And what you really want is this capacitor right across the gate to cathode, you know, to prevent any noise from getting into the SCR. Because you got to believe that the ground is jumping like crazy when you first power this thing up, because of the no inrush protection. So let's see. So here's the circuit, the entire circuit, the inrush and the input, the rectifiers, the filter, input filter, the closed loop regulator, and the OVP circuit down here. So that's pretty much it. I don't have anything else. Whoops. Damn. Sorry.
I got a question.
Go ahead.
When the SCR fires and shorts the output voltage to ground, that's going to draw a lot of current, right?
Yes.
What prevents us from burning out the transformer or blowing the fuse, or what happens here?
Yeah, there's an overcurrent protection circuit in the regulator. Let me go back to that.
I had the same question because that SCR is going to get
right
pretty
here?
warm, right?
This C2 and 3, CS and CL right here. Okay. If there's too much current, this area amplifier comes in and pulls down the output voltage, pulls down the current, the drive, kills the drive.
So what happens is there will be a lot of current, but the output voltage will be so low there won't be much power
Right.
going into the SCR, and everything's still cool, but we are shut down because we're output shorted and our current is very low.
Right. You have to go through virtually zero to undo the SCR. So yeah, this thing folds back the current, these transistors from conducting hard, but not folded back enough to get the turn the SCR off. It only takes a very, very small amount of current to keep the SCR latched. Right?
So
okay, maybe you could explain that word folding back a little more.
Okay. There is gain in this air amplifier. There's gain, and what happens is in the air amplifier, if there's voltage from CS to CL, it actually dominates the air amplifier inside, so that the output current is reduced.
I see. So folding back is kind of like making it work backwards, because normally when the voltage goes up,
yeah.
Normally when the current goes up, it just put out more current, but when we hit a certain current, it actually starts taking it way down low again because of this overcurrent circuit.
Exactly. If you didn't have this, you'd be blowing the fuse all the time. right? It would reflect back that power and pop this fuse.
It can.
Yeah.
I have an RS-35A that I bought in the 1990s. I'm still running my station with, I'm happy to say. But what are the most common failure modes on these kind of power supplies the person might run into?
Well, as I said, from what I've seen, from the two I've looked at, it's been the OVP circuit.
Okay, but I'm thinking like the big filler capacitor might die after a while or something, or not so much.
These are the capacitors they're using are very, very good quality.
Okay.
And you know, I've seen electronic equipment where the capacitors have failed, and it all depends on how your derating curves. In other words, if you run these capacitors in a hot environment, they tend to fail a lot quicker than and there's a spec on these things, on these capacitors, and what I typically, and I forgot what the spec is called, but effectively you derate the capacitor. It has to do with the heating, the self-heating of the capacitor itself. And I typically derate that. And a lot of these smaller products that are out nowadays, they run these things very, very hot, and towards the limit of these parts, trying to make the components small. But in this case, this capacitor is well within its capacity, and it'll outlive us. It's not running hot at all.
Okay, thanks.
But it's been so many years. There's an equivalent series resistance inside in the rating of the capacitor, and you want to derate that so that the capacitor does not run hot, does not run anywhere near its rated temperature. And if you can achieve that, then capacitor will last many, many years. That's why you buy a piece of HP equipment and it powers right up. And then there are other products you buy out there and you have to recap the whole thing. And it has to do with derating.
Speaking of derating,
yes.
So I noticed this has a 50% duty cycle at 35 amps and 100% duty cycle at 25 amps.
Okay.
I assume that is due to heating of the pass transistors.
I'm not sure.
Yes, that is correct.
Yeah, I'm not sure, but
it can.
Well, the transformer insulation has a limitation. Also, the wire it's getting hot, and it's usually a high temperature enamel, and at some point that becomes plastic, and the turns will short, and that's one limitation. And the other one is the capacitor. The electrolytic capacitors are much more sensitive to heat, and so they can make the barrier layer bigger, and they can run hotter. But then you have to have a bigger case and a much bigger capacitor, and your cost goes up. So it's all in engineering. It's all about finding the thing that's
derating.
Ideally, if you design something in electronics, when a part wears out, all the other parts will wear out at exactly the same time and all fail together. And anything that lasts longer by a millisecond, you've wasted money.
Right.
You're an optimist. Yeah.
So let's see, we got two questions out there. And actually I had a question. I'm going to throw mine out there. Is there overcurrent protection in this thing as well?
That's it. That's it. That's overcurrent protection there.
And that's in but that's in normal operating mode as well, right?
Exactly.
whether it's caused by the SCR being latched or by
Right.
just
Right.
an overload.
Yeah, that's right.
I have a comment. It's Matt.
Go for it, Matt.
Go ahead.
I have a large number of RS-20 power supplies in operation on a railroad, and some of those supplies actually pop the line fuse multiple times in the operation of where they were. And I was really puzzled why the line fuse would go bad. I discovered that in the industrial location where they were operated, there was a large fluctuation of voltage on the input. There were a lot of spikes on the input, and they use surge protection with a varistor, the V130LA 20A or 10A.
Yeah.
And oftentimes, some of the later ones I've seen, they actually moved that varistor out to a terminal and next to the fuse holder, and repetitively causing that varistor to react. They don't recover fully as well, and then they would go short, and they would continually blow the fuse. And you'd think, well, I've lost a power transformer. On some of those early RS-20As, they actually put the varistor underneath the wrap of the transformer, the insulating wrap of the transformer, right on the primary terminals of the transformer, hidden away.
Ouch.
And so if you don't see the varistor on the outside, is going to have one underneath that insulation wrap on the inside of the transformer.
Boy.
Yeah, it was a real head scratcher. Then again, I had one that, of course, these transformers are manufactured in Mexico, and sometimes they're a little careless, and actually found scrapes and scratches on the primary winding between turns. And of course, you couldn't keep it from blowing fuses. So there's some little quirks along the way that sometimes can lead you to head scratches. That's all.
So, all right. So I'm gonna, while we're thinking about that, from W7EAZ, has there ever been a situation in the feedback regulation loop where oscillation has occurred due to aging components causing an imbalance between the pass transistors?
I never discovered that.
Well, sometimes especially in the older supplies that had carbon resistors, over temperature and time, the resistors would go up in value. And so the circuit could change so much that it might, start to oscillate because of the, improper ratios between the various voltage nodes.
Most of the component values used in this are low enough so that resistance changes are not a high percentage due to aging. So they last a long, long, long time. Back in the old days, vacuum tubes and high value resistors, yeah, there was a lot of change due to aging, and those were kind of delicate construction back in the early days. These are a lot more reliable.
Now, I noticed on this diagram, you see on the right side where right below the SCR, you see the wires, the traces come together at an angle there at one point, and that usually indicates the reference ground for everything in the circuit, because all the currents and all the traces will cause voltage drops, but you want where you measure the output voltage and where your reference is to be accurate and not move around when currents change in the rest of the circuit. So you usually identify some common reference ground, and that's usually an indication when you see the traces come together like that. That's where everything should be measured from.
Right.
You have the ground foil, common ground foil on the regulator board. You have hardware to the output terminal and the negative terminal of the filter capacitor is screw mounted to the filter cap on that common on the board. So yeah, sure. Make sure that those screws, the plus and minus on the big filter cap, are firm all the time. The other points most often are hardwired terminals and such, and they're pretty reliable.
So here's an auxiliary question, sort of off topic. When I told someone this morning that I'll be attending an RS-35 Zoom presentation, I was asked whether they would go over the topic of bad components in the power supply currently, a large number of which are not working, and even when sent back to the factory, the problem persists. Any comments? I don't know what to say about that.
I don't know. I don't know any common bad problem. Occasionally, something goes guinea bag with the pass transistors, and they're not manufactured anymore hardly, and the people replace them with some of the cheap Chinese things at a bargain price, and you get what you pay for. And most of those are culls off of the production line, so they look all shiny on the outside, but they don't work.
Can I tell you a story? Can I tell a story, Ken?
Yeah, of course.
So, okay, do you know Gary AF7NX?
No.
Oh, you should. He lives up your way. He builds antennas. He spent his later life of employment building microscope stages. So he's and now he's a ham, and he does a lot of electronic stuff, and he needed some pass transistors, so he went and bought some Chinese ones, and he tried one out, and it went poof, and he said, okay, I don't trust the rest of these. So he has a website called squashpractice.com. He grows squash in his backyard. But anyway, as part of that site, he's got a ham radio section, and he bought a whole bunch of Chinese knockoff pass transistors. And he said, okay, I'm going to dissect them and not power them up. And he said, you expect inside a nice, good size case, like a 2N3771 in a big case. Is it a TO220? Like, which is the big metal case?
TO3.
Okay. He opened it up, and where you would have expected a big ass piece of silicon to be, there's this tiny little silicon. There's this tiny little thing with like 30 gauge wires connected to it. So somebody spent the money to build fake ones using a full size case and tiny little components. He said, yeah, no wonder it didn't work. And
Right.
he said, this is what eBay is flooded with.
Did you see the study the guy did on fuses from eBay?
I did not.
He put a couple of 2-amp fuses, hooked them to a power supply, and was able to draw 20 amps continuous through some 2-amp fuses. And then he started looking at various fuses after that and ran into exactly the same thing.
Mm-hmm.
It's just like a big bar and everything, no matter what the rating.
Wow.
Hey, just a general comment on components. Like if I was actually fixing my power supply, I buy stuff from DigiKey or Mauser, someplace where you can get specs and you know what it is.
Yeah.
Yeah.
Yep.
And names that you recognize.
Yeah, or even their names I don't recognize. At least it's probably legit.
No.
Okay, so can everybody see this? This is Gary's website. Counterfeit parts, eBay scammers, and Amazon shills. Wire, etc. Counterfeit transistors.
Wow.
And this is on squashpractice.com. And he lives here, right here in Eugene. All right, let's see. There was another question. Let's see. Do you have, let's see. Russ says, do you have the parts to work on stuff like this? And are you willing to work on them for money?
He's referring to me.
I think so. Russ, are you still here? Hello, Russ.
Yeah, are you a mercenary?
Mercenary. I don't know how that applies to this, but
You retired?
I do work on stuff. Yeah.
So if I gave one to Scott and he came down, you live close to Scott?
A few miles.
So if I gave Scott a power supply, he could dump it off into you and you could either fix it and charge me or say it's worthless.
Kind of like just drive past his house and toss it out the window of the car.
Yeah, leave it on his front lawn.
No, I wouldn't do that if I would. I'd put a hole in my front yard.
All right. Oh, it's so heavy, nobody's going to take it. Although it's probably worth something in scrap, right? I bought
I've got probably 3 of these that don't work. So if I gave you 3, could you give me one back that works? And you can keep the other 2 for parts.
Both of these are all RS 35Ms.
No, one's a 35, one's a 20, and one's a 5 or something like that.
I think it's probably a 7.
Same.
Maybe it could be a 7. I don't know. I haven't looked at them for a while.
Yeah. Well, I'm getting used to them. This is my second one here.
Yeah.
I got to fix this one for this guy that let me borrow it.
Yeah, I've got a couple others that do work, and they're good for charging the car or keeping the lawnmower charged over the summer or over the winter.
Yeah, that's what I use my old grief kit power supply for. Charging my car.
Okay, Jeff Kelso, you still there, Jeffrey?
Yeah, I'm here.
All right, Jeffrey, you want to talk about your story?
Yeah, so I bought a what is it? A RS20S, excuse me, 20S, and I knew it had no power output, so I bought it for all of $10. And I went to the source of all knowledge YouTube and basically replaced the IC and the 2 transistors on the back, the 2N3771s. And lo and behold, when I turned it on, I got 13.6 volts out the back. I was just tickled pink that I actually fixed something for once instead of broke it worse. And then hooked my 2-meter radio up to it. But when I keyed up my radio, that was the end. And so now I get 0.4 volts out the back of it. Do you have any other ideas about what might be going wrong there or what I might need to replace?
That sounds like the SCR at that point, doesn't it?
It sounds like, well, yeah.
But now what happens if you power it down and turn it back on?
I still get 0.4 volts.
Okay, so resetting it doesn't work.
Could have,
Right.
Could have been the RF that triggered the SCR. How close was the radio to the power supply?
And you did key up, so that generated RF.
Yeah, and but it still didn't reset the SCR. So
No, it could have taken the SCR out too.
Right.
okay.
Yeah.
So
all right.
Was the antenna indoors or outdoors?
It's indoors, but it was, I don't know, 20 feet away from the power supply.
That's probably okay. Low power or high power?
It was low power. I think I had the radio on 5 watts.
I don't think so.
Yeah.
I don't blame the radio.
No. At that point, where do you look?
It still sounds like the SCR though.
Hey, just unplug it. Just take a ohm meter on the output and see what the resistance measures.
Shower's yours anytime you wish.
Thank you.
That's good to know.
If the SCR is shorted, it will not latched, but shorted, it will read very close to 0 ohms between the output terminals.
And the SCR goes directly across the output?
Yep.
Okay, I'll put an ohm meter on it here real quick.
Yeah.
Just make sure you turn it
Although
off.
the SCR would get toasty if in the
Well,
crowbar mode.
If the SCR is like the other one I worked on, it virtually has no heat sink. They just have a aluminum heat sink screwed to the transistor or the SCR.
Yeah.
They don't have a thing like this where it's tied to the boat anchor.
If they're operating properly, they go essentially short for a short period of time. The fuse blows and they don't build up any heat.
Yeah,
Yeah.
absolutely. Protect themselves.
So, all right. So here's a question for you. Having been through a period of big linear power supplies and also switchers, the original switchers that I would find were known to be noisy. Of late, most of the switchers that I find are really, really, really quiet. Do you find that as well, Ken? Has there been a change in the industry?
Absolutely. Absolutely. There are standards now. When I first started designing power supplies, they I did my first one and they said, well, wait a minute, you need to meet VDE standards. That's the German conducted radiation standard. So they sent me back to Chicago to design a EMI filter to put on the line so that the conducted radiation was in spec. And so there are quite a few standards out there right now that these guys fortunately have to design for that's really helped the industry significantly. Yeah.
And you think a lot of it comes out of the CE specifications for
Yes.
emissions?
Yeah, you have to go through, you take it, if you design a power supply in this area, you need to take it to Portland. It goes into a screen room and they check it for radiated and conducted emissions. So yes, there's a significant improvement in that industry.
Even stuff coming out of China?
Don't know.
Don't know.
I mean, that's a crapshoot.
Yeah.
Whether
It
they
depends.
really
If it's
use it or
designed to meet
not.
specs, probably okay. If it's not
Mhm.
designed to meet specs,
Yeah.
probably not okay.
Well,
Yeah.
right. And that's kind of like, Motorola radios for a while were still made in China, but they were made to Motorola specifications.
Oh, that's
So
You can
fine.
buy stuff from China that's as good as anywhere in the world.
That's
You
right.
just have to pay for it.
Right.
Ken, I've had a 35M since 1970, and it's still operating perfectly.
Yeah. No, you got lucky.
And I've got a 50M that's been on for about 10 years now,
Continuously.
continuous. Other than power outages,
Yeah.
I only turn them off if we're going on vacation.
Yeah.
So Ken, you were when we were talking about it, you were saying that the design is good, but sometimes it comes down to the execution. And I think there's a lot to be said for that. I'd like to hear more.
Yeah. Yeah.
So what do you got as far as the design being good, but execution and how things are bolted and mounted and things?
What do I got?
Yeah, what do you got? What's your opinion? Because you told me that what you were seeing was poor execution. Things not being built the way they really should be, and that being the problem rather than the design.
Well, I think care and feeding of the power switch. You don't want to have the power switch going on and off. Turning it on and off at a rapid rate to increase the surge. You could take out his MOV, Matt's MOV, quite easily by getting some spikes. And it's very hard for me to predict.
Well, just as far as you said that, sensing things that are used in a sensing circuit, they really need to be local to the devices as opposed to
Oh,
far
are you
away.
talking about in design?
Yeah, yeah.
Oh, in the design of the circuit, not in the actual RS-35M.
No, just in general.
Well, in the design of any of those Astrons,
Yeah.
the studs coming out the bottom that are hot, that was an
Oh, yes.
unbelievable
I have
bad
done
design.
that. What's up with that?
Well,
I've
because
done that.
They put
they
plastic
insulated
over
the
them sometimes,
diodes.
but
You know, they want the heat. They want to dissipate the heat, but they obviously can't have it connected to the ground. And so if you go along and take those bolts to ground, yeah, that's a
I've
problem.
accidentally done that.
Yeah,
you don't want to touch them.
they're hot.
Seems kind of dumb, doesn't it?
It seems like it's not UL approved.
Well, my guess is that because my guess is, do these things have a UL approval? I've never really looked.
I doubt it.
They pretty much have to have UL approval if you're going to sell it in LA for sure. That's what started everything. Is LA decided that no UL approval, you can't sell it in LA. That's when UL got their teeth from Los Angeles. Up until then, they were just an outfit that investigated for insurance companies from Mrs. O'Leary's cow.
Okay, let's see. Astron RS 12M BB power supply meets UL, CUL, CE, and TUV. Okay. Well, there you go.
Yeah,
So-
probably now they do. The newer ones probably
Have to
don't
have.
have the studs in the bottom.
Yeah.
Now they get away with the studs in the bottom by the insulator. They have feet. Feet on the bottom that keeps you from theoretically from grounding it. You didn't have feet on yours?
No, got feet on that. But if you had something on the desk and you put it down on the desk,
right,
a non-flat surface,
right,
or if you reach down with your hand, that's live juice.
Yeah,
Not that
not that-
what is it? 20 volts will going to kill you, but
not that high. Yeah.
In fact, below anything below 24 volts, UL actually doesn't really even care about, at least in industrial stuff.
Well, they care about the amount of energy for some of those things. If
For
there's enough
some,
energy
yes.
to melt stuff, they care.
Yeah.
They could do that.
When you're getting your UL testing done, you're prohibited from having any flaming or molten stuff come out of the case. I know that.
Mhm.
They don't like that.
I don't like it either.
Well, they're picky.
I work with UL. I don't like it when I have that either. Usually means something went very wrong. Okay, let's see. Other questions or comments from anyone?
Yeah, I got one. This is Scott, NA7OM in Medford. What I found on a couple of them is that over the years, the heat sink compound kind of dries out on the back of the pass transistors. And
Yep.
a simple check with with a finger, for example, you can find out which one's hot, which is cold. But usually when that happens, when you take it apart, be careful the mica spacer. By that time, the heat sink compound is dried out to the point where there isn't any effective heat transfer.
Actually, worse.
What are your thoughts on those pads that are for heat transfer instead of the compound?
Well, I know what you're talking about. Some of them, not mica, but the silicon ones, they do a good job. Again, it's all derating. In other words, if you'd like to design with one of those, make sure that the thermal conductivity is adequate using it. But the good news is that it will last forever. It won't dry out like the compound does. So it actually, it's desirable to try to use those. That or mica. Yeah.
Oh,
Very
Micah's rock,
desirable.
so
Because as I said, they will last a lot longer than the heatsink compound.
For a while, those thermal transfer washers were made out of beryllium oxide. They probably don't do
Oh,
that
that's
anymore.
fabulous. Yeah, really, using beryllium is great.
well, as long as you
You
don't
don't
like
want to scrape it
inhale
or
it.
anything,
Yeah,
but
yeah, it's
Yeah.
just really
beryllium has a
poisonous.
very low thermal resistance, very good. But again, you know,
Kind of toxic.
there are
Yeah.
issues. Yeah.
All right. Anybody else with anything else? I guess not. Well, so Ken, I've been asked by a couple of people. Whoa, somebody's audio's.
Somebody's
Mark, your audio is kind of messed up. You might disconnect your camera and then reconnect it.
Yeah, we found this out.
Yes.
Yeah, go ahead.
So is there a recording going to be made available? Because this is being recorded.
Yep.
And I've had numerous people ask that they wouldn't be able to make it, but they'd love to be able to watch it.
So you have it, right? Since you're the host.
I think I am. So I will make that available, and you've
And
got
I can make the slides available.
Yes, you can send me a copy of the slides. That would be great.
You got it.
All right. Is there anything else? Mark, if you want, go ahead and type your question.
Well, you guys know where I live. If you have
All
any issues, let me know.
Mark is typing a question now.
So for a future topic, I'd be interested in knowing people's experiences, good or bad, with various switching supplies and also inverters for emergency power.
Okay, is there an inrush current modification that you can think of?
Sure. I prefer in this case the resistor relay solution. Okay, so what happens is you have a resistor in series with the input, right? Where the fuse is in series with the fuse, let's say. And then you have a relay, and the relay coil is powered by the output. Right? So when the output comes up, then the relay closes and you can draw full current.
Okay. Right, because you won't have okay. Because you won't have enough voltage at first to actually activate the coil
of the relay.
Right. That's what it's designed to do.
Yeah.
And so the resistor limits the current, and then when the voltage comes up, the relay pulls, closes the contacts, and short out the resistor.
Yep.
What do you think about running the relay coil off the filter capacitor instead of the regulated output?
Where?
Hook it on the filter capacitor before the regulator.
Sure.
But again,
that's where the current inrush is really happening.
Right. But again, this one, Mark says mine clunks all the time. And I've had these for years and mine do also for that very reason.
Yep.
Yeah. It's not a big problem. I've never experienced a whole lot of difficulty with that with 30 RS-20s, and I've got an RS-50 and VS-20 and a VS-12, and I get along with them pretty well.
You don't turn it on and off very often, no?
Yeah, no, not every day. No.
Right.
So here's my impression of all these power supplies. You hit the switch and it goes and it vibrates in your hands.
That's right. Yeah. Bong.
Bong.
And Yeah, but so what?
Oh, right. So long as it's not damaging anything, it's okay.
Well, obviously Astron thinks so what?
Yeah. See, I always assumed that that was that the inrush was being basically magnetization, and it was slamming the cores, slamming the lamina in the core together just briefly, which it may be.
Well, the humming is because of magnetic effects, more than likely, yeah.
Right. But the
But yeah,
the
yeah,
bong sound.
But the high current is because of charging the cap.
Oh, right, right.
yeah, definitely.
Well, thanks, Ken. That was really interesting. I think I'm going to go recline.
Go around the loop.
All right. If nobody else has anything else, I'm gonna go and save this, and I have a YouTube link that I can put it up to and pass it out to everyone. I've got everyone on the mailing list.
Okay,
Yeah.
thanks, guys.
Yeah.
Scott for the host and Ken for your input. That's really greatly appreciated.
Yeah,
And
we'll see
and
most
Ron
of you at the DQ.
and Ron for being the coordinator. So, Ron, would you like to throw out another pitch by chance?
Oh, he's got his camera up too.
Yeah.
I'm sorry, say again.
Would you like to throw out just a pitch in case anyone knows anyone who'd like to be on the technical committee for the section?
Okay. And you want me to say something now or
Yeah,
throw it out?
you got the floor.
Well, we'll accept anyone, we're very open here. There's so many different kinds of technical problems that hams have, from HOA restrictions and uh, noise problems from neighbors. Now I talked to a guy a couple nights ago, and he has a neighbor. He just moved into the neighborhood down there in Salem, Southwest Salem, and he checked out the neighborhood before he bought the house, and it was very, very quiet. And now he gets these blasts of noise. And I went on Google Maps and I looked down at his house, and right across the street there's a roof covered with solar cells, solar panels. So I thought, okay, there probably is a big inverter in there, you know, uh, uh, what do they call it? Maximum controller, and it's a big
MPPT.
switcher and making all kinds of noise for them, that kind of thing. We need people that uh, can help look for those kinds of problems and steer people in the right direction. And a lot of it you can just do from home, just answering an email or sometimes a short telephone call. But we need every kind of expertise. We need people that are just getting started in emergency services. They've got that mostly taken care of with the classes. So that's fairly important that be procedurally correct. But for most kinds of things, the newbies in amateur radio, they've never put an antenna up before. They don't understand about the names and numbers of the connectors. They've never soldered before, and they're afraid to solder, and yet they need something soldered. All kinds of very simple things that are common technical knowledge you pick up over the years, and you could be a great help to someone by paying that forward, by helping other people get on the right track with their problems. Anyway, that's what the technical specialists are all about.
So go and spread the word, everybody.
Nice. Good job, Ron.
Hey, Scott, what's wrong with my audio? Is it working now?
It's working now.
Great.
Yeah. Blame it on Microsoft.
Yep. And Ken, what's that in your lap?
That's my dog, Abby.
And Abby is a poodle
Golden
mix?
Doodle.
A golden doodle?
Yeah.
Aw. Does that mean it's time to take her for a walk?
That's a very smart dog. Those doodles. I had a Labradoodle. Oh my goodness, so smart.
Yep.
All right. Well, thanks everybody. And think about ideas for other topics. And I think, this is it's a good thing to do. And if you're not subscribed to the to the Oregon Technical Group mailing list, we have a groups.io list, and you want to be. It's let me just find it. ARRL Oregon Technical Group, not Oregon Oregano.
Hey, everybody, let's give Ken a big hand.
Thank you, thank you.
Yay, Ken.
I can't hear you clapping though. I can see you clapping. Air claps.
Air claps. So this is I just posted the name ARRL Oregon Technical Group. And cool. Thank you so much, Ken.
All right.
Scott,
Yeah, Steve. You're muted, Steve.
two comments. If you can't hear people clapping, that's the deaf means method of applause for whatever it might be. And my second point is in the future, if Ken could somehow have split the screen and had a schematic diagram to go along with, that would have been infinitely helpful. I have an RS-35 Alpha. I've had it since the 70s. I've had to fix it once. One of the output transistors in the SCR failed, and when when one output transistor failed, my mentor suggested that if one of them had failed, the others had probably been stressed, and I should probably replace all four of them, which I was able to do very easily because in those days I lived in Southern California, and there was a well-known electronic surplus store that was able to get the exact identical parts for a at a good price. But so that's I guess my big comment would be if we could somehow split the screen and have a schematic available so that when he was saying Q1 or whatever, he could point to it in the schematic. Unfortunately, I had a schematic once, but I think I've lost it in the 30 odd years that I've had mine.
Okay.
Ken, do you have a copy of a schematic you can send along with the slide
It's in the
deck?
presentation.
There you go.
I thought
Yeah.
I had it.
Yeah.
Yeah.
I was looking at it, so.
Yeah.
Okay.
Well, I was, for whatever it's worth, for some reason, I was unable. I could see all the pictures, but I could not see the schematic.
Interesting.
Yeah.
Huh. Well,
Good to know.
Get a copy of the presentation, you'll see it in there.
Yep.
Yeah.
Okay, just thought I'd make the comment. And
Sure. No problem.
for whatever it's worth, I have a friend in BC who does a lot of heat transfer and sells his own heat sink for the KX2 and 2 and 3, and he advocates against using heat sink compound on the and his intelligence behind it is, if you don't know what you're doing and you don't do it carefully, it could often be worse than none at all.
Yeah, it's process sensitive.
Yep.
Yep. Absolutely.
All right.
Yeah, the thinner the better, by the way. Yeah. Okay.
Well, thank you, everybody.
Bye-bye.
Have a wonderful night. Thanks, Ken.
Good night.
And thank you for setting this up.
You bet.